Hello guys, welcome back. So we finished our last class here, and today is very important because mostly we gonna do all the remaining tasks today if time permits. So what are the remaining tasks? One is we need to route it, right? Second is we need to do the simulations for our layout. So for that we need to install NetGen if it is not there, and if it is then great, but I will try to install it because I don't have in my system. So we need to install NetGen, and in thirdly we need to do the LBS, right? So for LBS only we need the NetGen, and then we'll do the simulation and we'll see the result. Like we'll try to compare our result between the schematic result and the layout result, and which will be very interesting, right? So I hope you are excited. If you are, then please like and let's start the video. So before I go for the layout routing, I want to clear one concept here, which is mostly used in the practical design. For example, see, in practically in industry or anywhere where the big circuits are designed in the layout, so we have many such kind of blocks. In SoC, system on chip, we probably have a memory block, right? We probably have a interface block, analog interface block. Then we might be having some CPU block. So those blocks are designed by some separate team, right? Inside memory blocks also there will be many things, and those will be again designed by separate engineer. So if you have two block A and B, you are designing A and I am designing B, right? And we don't have any communication between each other, and what you did during the physical design, you design your metal 1 with as 1 micrometer, right? And what I did, I designed everything and my metal 1 was of something like 2 micrometer. But finally these two block will come inside one chip, right? So anytime I'm gonna integrate these two, what result I'll get? I'll get a 1 micrometer here, and when I integrate my block, then I'll get a 2 micrometer M1. So this kind of things might be allowed but might result on DRC, right? So there would be an integration engineer who gonna integrate both the block, and he or she will have lot of work to do to clean those DRC. So why to create those DRC in first end? And therefore we have something in everywhere, and that is that we first decide some standard guides, and those guide will help us to determine the width of our metal. So roughly what we have in practical design, and those are like we will decide that hey, our power routing would be of some width like this 1 micrometer, and then we'll have some track for our signal routing like 3 tracks, and then we'll have another power route which will be of 1 micrometer, and signal probably of 5 micrometer, and in between these two power separation, and might be it is for example 10 micrometer. So if we have some kind of standard rule defined in our layout EDA tool, then anywhere anyone can design anything, but anytime we're gonna integrate it, for sure our block A power line will exactly coincide with block B power line, and which that's what our goal is. And this is a really wonderful insight into the practical design, and I got this insight when during my MTech I took one course which called semiconductor memory design. So there our course was 80% of practical designing only. So we used to have 5 or 6 people group. We used to design separate block, and there the instructor he introduced to me this concept that hey, we in industry we have this type of defined guides, and after guides are defined, then only you need to do your designs, right? So in some EDA tool we have the facility to install those instruction, so that the designer will see some track like that. It will be like dot dot dot, you know, hey, here only I need to draw my metal 1. But probably in Magic we don't have that, so we need to manually do that. I need to explore in Magic if we can install those guide information or not, but currently I'm not sure. And apologies for any noises you are hearing, because if I wait for the perfect time, then I don't think when gonna I shoot this video. So please ignore those noises and let's concentrate here. Okay, so we're gonna first connect this, like we need to do our inverter design. These are PMOS and NMOS, they are separated, so we need to connect them. So as we know, this is a symmetric device. We can consider anyone as drain, anyone as gate, right? But for our simplicity, what we'll do, we will consider this as our drain, this is our drain, and this is our source, this is our source. So just remember, for PMOS, where should your source be connected? Your source should be connected to VDD and to VSS for the NMOS, right? And this is our body connect for PMOS, this is our body connect for NMOS. Body connect for your PMOS need to connect to the VDD, and your opposite is for NMOS. So what we're gonna do, we will assume that this is our power track for VDD and this is our power track for VSS. So let me draw. Why should we assume? Let me draw it. Okay, I want it, okay, let's do it roughly. So I'll write paint M1. So we're gonna do our power routing with M1. Locally it is M1, but anytime we're gonna use it in our SOC or in our any other blocks, those would be on M5 or M6. We'll connect using VS, but in locally it will be on M1. Okay, so this is our VDD track. So as I said you, this is our power track, right? Here no guides are defined, but we will assume that some guides are defined. So if these are our power track, then in between the power track we will have our signal track, and in your inverter we have two signal mostly. One is your input, another is your output. So for two signal requirement, how many track are required here? In roughly sense, we can say hey, at least two, in between these two there should be two signal track, there must be. If there are more, that's great, we will just ignore them, we won't be using those track. But I think we only need one track here, because from here this will okay, let me design and then you will understand. Actually only one, like we will use only one track of signal. If there are some other track are available, those will remain empty. Okay, so after we define our VDD and VSS, but how we define? We just drawn it, right? How our tool will know that hey, it is a VDD or VSS? So for that we need to level it, right? So for leveling it, let me zoom a bit here. Yeah, let me zoom. Okay, let me go up. Yeah, so for leveling up you need to define a point, roughly a point. So what you will do, you just select a point, you just right click and left click. So you got a point, and then you come to your command prompt. See, this is your command prompt, just keep a eye here, and here you write level, and what I need to level it, I want to level it as VDD. We can't see anything here, but if you zoom in, you can actually do the things that hey, I want to see it, like I want to increase the size of my letters, but these all are like not required right now. So and I also don't know, I need to explore how to increase the size of levels, but you can see it here. I think if you don't see still, then now you can see it, right? This is our VDD. Okay, let me go out and I will do the same thing for here. So VSS also got defined. Now this is my body connect, this is my metal one, right? But if you just remember yours, okay, let me get the stacks. So this is your stack. We have a M1 and we have local connects also. If you remember, in when we are creating our body connect, we need to use LI, local interconnect. So we have LI, we have our M1, but in between there is no connection, dielectrics are there. So we need to insert a VIA whose name is mcon. So we will do that. So I don't know the exact dimension, so I'll roughly select something like that, and if DRC will flag, then we'll fix it, and I'll write paint mccon. It was mcon, right? Mcon. I hope it will work. No, it was not a. Okay, it is not finding paint mcon. Yeah, it is mcon. Luckily we don't have any DRC also, that's great. Let me do same thing here also. Actually we love to have some symmetry, but right now I am not looking for any symmetry, and it is not required for our functionality also. If it is, then we will look for symmetry. So now how, okay, let me do the next step and then I'll share that. Okay, so now this is your source, this is your source, this source need to be connected here. So how to connect it? You have many metal layer, you can use metal 3, metal 4, any metal layer, but why to use those metal layer? We can use it for other tasks, right, outside this block. So we will use the lowest most one, and that is LI only, and that's why local interconnects are defined, LI. Luckily I hope there is no DRC yet, and we will do the same thing for this guy also. So now let me remove the grids here for a moment. Now there is one very great functionality in Magic we have to know that if things are connected or not. You remember it, right? This is our VDD. So I want to know that hey, this VDD actually got connection up to the source or not. So for that, what I'll do, I'll just click here and I'll do S. S will select M1. Then if you again click S, it will select little bigger area. And if you again click S in your keyboard, then it will show you everything which are electrically connected to this level VDD or this net mostly. So if I again select and see, it is showing me this anything net name. Now it's VDD. It got a nice connection up to the source. If you do here also, first it will select this, then again yes, it will select the whole, and then again yes, the whole electrical connection. So it's a nice way to understand if things getting connection or not. So that task done. Now if you remember your inverter, your two drain need to be connected, so we will do the same task here. Let me have the grids here again. So for output, what I will do, again output, we can have output on Li, but it is good to have output on M1. Now you will question me, hey, how you know why you are using Li somewhere, M1 somewhere. You can use any metal there, as I said, but anytime you design a big block, you do metal distribution first. Metal distribution means you allocate your metal. Like I have 5 metal layer, so I will tell all the project mate 5 or 6 that hey, M5 is reserved for that, M6 is reserved for that. So probably here during this project I said to every my project mate, hey, for any input and output from a standard cell, which is your inverter, M1 would be there. So this is the out now. I'm getting signal out from this block to the other world, the outer world, right? So I will do it with M1 only. It is on me actually. I want to use it. You can use any metal layer, no issue. M1. Okay, so again concentrate. This is your power grid, this is the power grid, and probably anybody who has defined guides for us, they said hey, this is a track available for you of this much width for a signal track. So this is a signal track, right? So this signal track got used, but this signal track is running from here to right side. My left side is still available, so I can use my left side for my input. So that means only one track is all okay for designing an inverter. So what I will do, let me do one thing. Let me zoom in M1 and see we have a DRC here. And what's DRC? DRC, one option is that, as we all know, we'll go here and we'll know that hey, metal 1 spacing should be more than 1.14, but it is not. So we know the DRC, and what's the alternative? We have a way, and the way is that you can use a Li here first, a Li here, and get it little left side, and then use the M1. Okay, so let me erase this part from here. So we will write erase M1. It is done, and we will paint here Li. But see, Li also not allowed. After I inserted Li, there is a DRC, and that is same error. Your two Li can't come too much closer. So you undo. So what's the way around? Way around is that hey, use the poly only. Mostly we don't want to extend our poly because poly are high resistance things. But here there is no way, so we can extend a little bit, and then we will take the help of M1 to interact with the outer world. So let me take it up from here. Poly is done, and here let me increase my metal 1 up to there so that I can use a via here. There is no DRC, that's great. Now what's the connection we should use? We have a poly, we have a metal 1, but poly metal 1 in between Li need to be there, right? So that's why I will also paint, and then I'll use poly to Li. Like poly to Li there should be. So if you're confused, you can refer to your stack layer, PDK stack layer, or as roughly we know that we will have something called poly connect, poly C, and see poly connects, it's there. But I think poly connect have many DRC. So let me go to window. So it is giving me one error which we already have tackled, right? and another is poly overlap poly connect. I know the error. You can again go to your PDK document, you can see the figure if you want, but I know, so I'll fix it quickly. Poly overlap of poly connect, that this is little I don't know, but I know. I think one thing we can do, and that is do U and then just select a little less area for this, like this much and this much, but it will be very but let's try it. Paint policy poly connect. Wow, there is no DRC. I'll show you. Update, there is no DRC, right? Okay, but still I think it is not connected to M1. How to know it? Come here, see, it is not connected anywhere. I am clicking S on my keyboard, but it is not going anywhere. Ideally it should connect to this gate area, this poly area. Why? Because now my poly is connected to LI, but to connect LI and M1 I need to again do the MC con, right? So paint MC con, and now if I do the same exercise, S, everything got connected. I'll do the same thing here, or I can do one thing. I can just copy this fellow, or let me do one thing. Let me to select everything here what I said to you. Okay, so here one thing you can observe, that our selection is still there. I want to just get out of my selection. You can see this highlight, right? It got selected, that is showing me connection. So to get out of those selection, you can click comma on your keyboard. So comma and everything gone out. Now I want to copy this fellow to here. So to do that, what I need to do, I need to select a box. I did same thing in last lecture, you know it, right? But yeah, and then you need to press A on your keyboard. Pressed A, and then you need to get your cursor. Let me zoom in if I can do. Yeah, get your cursor, place it roughly somewhere where you need to place this copied thing, and then press C on your keyboard, and we got it. But we have some DRC, so to avoid this DRC, I know this DRC is because here we have very less space. So what we'll do, we will copy this thing little right side, so we'll be for sure there is no DRC. So I'll do U, I'll come here and I'll press C. We are again having something, and this DRC, because here we have LI, here also we have LI, but in between we don't have any LI, so there should be some gap, minimum gap we are not maintaining. But here we don't want any minimum gap, we want to connect this LI to this full M1. So what I'll do, I'll just close this space here. Okay, after closing, what is the DRC? End diffusion spacing to annual. End diffusion spacing to annual. Why it is coming here? Oh, okay, I got it. Do you actually, I came here now and I press middle mouse button, mouse button, and what middle mouse button do? Middle mouse button copy everything, like any layers are there. So here we have two layer na, LI layer and our annual. So it copied LI and annual here, so that's why we were getting the error. So don't do that, you just select it and then do a right paint LI. Now see, we don't have any DRC is clean. Okay, we have progressed a lot. And to see whole layout in one window, press V for victory. Not here, come here and V for victory, and G that I want to get out of the grids. Okay, so we have VDD, we have VSS, but we don't have defined this, right? So I'll do again, but here we'll do little different thing. These are the levels, right? These are the levels, but I want to define the port. There is a difference between port and level, and sometimes both things are similar only. But for now, just understand why I am saying this port, because I will use, like, powers are always everywhere, so we don't need to define any port. If we have it defined as port, then anytime we will use this layout in our bigger block. For example, we are designing a buffer. In buffer we need two inverter, right? So that time that port will help us in our future design. You will see that. Okay, so to define your port, you just need to select a small box here, and then you need to do the same thing here. Level, you are seeing it right here, level, and then what it is, yeah, it is the output. So out, level in got. So if anything not got defined, then in the netlist we'll get it up. And why to do the netlist? If you are confused, then let me explain you. So we are using a lot of tools and you might get confused. We used our Xschem, right? Xschem for X, and then we used our magic VLSI for the physical design. This is for our schematic capture and this is for our physical capture. But these two things, like the result of these two things, need to be simulated. And who will do the simulation? Simulation will be done through your Ngspice, which we already saw whenever we were doing our schematic classes, right? And Ngspice support .spice file. So that means from both of these schematic and from layout, we need to have a file or we need to have a code, because computer only understand code. So we need to transfer those symbols from the schematic to some code, which we already did when doing netlisting. And also in layout we have many polygons, right? So we need to transfer those information of polygons to some thing, and which is again called netlisting, and that only we're gonna do. So now we have both, for both we have the spice. Now we can compare the result, right? Okay, now that's great, but where the netgen is coming into our picture, right? You have this question. So see, to compare both your layout and a schematic, netgen is not required. You can compare them using these two tools, actually three tools: Ngspice, Xschem, and your magic VLSI. But somebody need to tell us, right? Hey, the schematic and the layout are coinciding. You are doing the same thing what you have done on schematic and on the layout side, and that's where netgen is coming. Because netgen, what netgen will do, netgen will take dot spice from your Xschem and from your magic, and then it will compare and it will give you the result. If it is clean, it will show head screen. If it is not, it will show you need to do some work. And yes, netgen is still not installed in our system, so we will do that. But before that, let me have my netlist. So for netlisting, what we'll do, before that, the important thing, save your design. So go to file and then save. When you click save, you will get some window like that, and you click write, so it got saved. Then you write here extract and then all. So it got extracted, and it got extracted as this. This is a type of netlist only, .ext, but as I said, we need to have a .spice. So for that we have one utility, and that is xt2 spice, and then give this name here. Okay, it is not coming. So layout day2.ext, finished. And to verify if this got created or not, we will go to our Xterm. Let me bring it here. This is done. Where is my Xterm? Yeah. Bring it here and just write ls-lrth to see the latest thing what got prepared, and you see this is the latest thing, spice. So let me open it up, and it will be very insightful when you see what inside there. It is very insightful. Here you also need to remember our schematic classes whenever I explain our spice. If you are don't familiar with the spice format, then you will face difficulties here. So for that, please revise those videos. Xschem, there I have explained everything in deep, like how spice actually, like what things are there. So I am assuming that you know, like you already gone through those things. So see here we have x0 and x1. So x means we are using something from outside. So here something from outside means this PMOS and NMOS we are using for our inverter. Technology is also written here, and like your drain is connected to out, your gate is connected to in, and then your source and the body connected to VSS. This is for NMOS actually. In NMOS we did VSS. And how to know this is NMOS? See here the model, actually model name is there. It is a NFET, right? And what are those? AD, PD, AS, PS. So AD is your area of drain, PD is parameter of drain, AS is your area of source and parameter of source. Our W is 1 and our L is of 1.15. So these all are in micro. That's great. And it is also getting the same thing, like we wanted to develop a NMOS of W1 micro, and we are getting it. So that's a good news. and you can just verify here. Some issue is happening. See, our W, it is showing 2.1 for our PMOS, which should be 2, but let it be here. We will investigate. Actually, this dissimilarity should come in our LVS result. So this is a great use case, test case, to see if really LVS is working or not. So let it be for now. And yeah, our length of the PMOS is 0.5. That is correct. All terminals are also good. And here one capacitor also got created here from VDD to VSS. I'm not sure how it got created. Is it the parasitic capacitance or not? But for now, let it be. We will investigate it later in later phase. So now what the task remain here? If you just remember your Xschem lectures, there I said this is something which is written in English, right? In English it is written. Our computer don't know. If I try to run this spice using my ngSpice, for sure ngSpice will highlight that, hey, I don't know what is my sky130. Please tell me what is that. So for that, what we need to do, we need to give them the library link using .lib, like from where you can fetch the definition of this word, right? So we need to give here .lib, and then also we need to tell ngSpice what simulation we're gonna do, DC simulation, trans simulations, right? And also we need to give the power source, like what is here VSS and VDD is written, but what's their amount. So we need to define all those things. So for that we need to define a test bench here. We can do test bench in our schematic. In the Xschem classes we have done for the schematic, but for layout we can't do it in our schematic, right? So what we do mostly, we do in the spice model only, because finally anything you do in schematic need to go to spice format. So what here in layout we'll do, we'll generate a test bench, we'll code a test bench here only using .spice language, and then we'll run it, and we'll compare between the Xschem ngSpice result and Magic ngSpice result. But before that we need to do the LVS also. This is a very small circuit. LVS is not required actually. By visually we can see that everything is perfect here, and we also said that this is a wrong thing. But for a test case to see how LVS is working using NetGen, we need to do that, and we will do that, but not today because it's already too late. So please do this homework, and for sure I'm getting you the 4th part of this video very soon. Till then, subscribe if you not, and keep learning, smiling and helping other. Tata, bye bye.